perhaps with singularities. These correspond with meromorphic flat connections, which, if you trivialize the bundle, they look like this, where this is a holomorphic Lie algebra valued function. So, and we saw that these are the same thing as representations of the Lie algebroid T. So we're on a surface, X is a Riemann surface, and D inside X is a divisor, which is just, let's say, a sum of points. And there was this funny Lie algebroid, this confusing, useful Lie algebroid, whose representations are exactly these meromorphic flat connections with poles bounded by D. So, this is something that we encounter all the time. Linear, ordinary differential equations, systems of them with poles along a divisor on a Riemann surface. And these things have a representation theoretic explanation or incarnation as representations of this object. And we saw that actually this Lie algebroid has an integration to what I called the twisted fundamental groupoid, an example of which was the Stokes groupoids. And the Stokes groupoids are the ones where you just have the complex plane and a single divisor and a single point, right? And this groupoid is then this explicit one that I gave last time. Okay. Now, so I just want to say a few words about these representations today.
May I ask a question?
Yeah.
How the degree k reflected on the representations over there? Because it seems that the right side is independent of k.
K is, you see, this is a pole of order k at z equals 0. So z equals 0 is a special point.
Okay.
And that point is the divisor. And that divisor has a multiplicity.
Yes, but on the right-hand side, I don't see any degree of this.
Indeed.
So
It's independent.
You're right, but you should allow these points to have multiplicity. So for example, if the divisor is of order k, then it will be p plus p plus p k times.
It is hidden inside D.
It's d. D is the divisor, and it tells the order or the maximum order of the pole. Yeah. So basically, when you're given an equation, what you have to do is you have to look at where the poles are and how strong are the poles. And that tells you which groupoid you should be working with. Okay. And that tells you how to proceed. Okay. So, so again, what are these representations? So we have right. So what is a representation of a groupoid in general? Of a Lie groupoid in general. So again, let's say that the groupoid looks like this. Right? We have the arrows, which have source and target in X. And then we have a group. Let's say, let me just take a simple example of GL RC. This is a group. I can think of the group as a groupoid over a point. You can think of elements of any group as being arrows which begin and end at just a point, a one-point set. Okay? And to have a representation of this groupoid just means that you should have a homomorphism of groupoids. Okay, but right. So, what does it mean to be a homomorphism of groupoid? It means that if you have two arrows in the groupoid, G1 and G2, and you have their composition, then it should be that the matrix that is assigned to the composite should be the product of the matrices of the two individuals that we're composing. So this is the condition. Okay. Now, let me just rephrase that condition in a slightly different way. So whenever we have a groupoid, this has what's called a nerve. A lot of people have nerve, but this groupoid has a nerve. And this groupoid, the nerve, it looks like this. You start with X, you have G, and then you have what's called G2, and it continues after that. And what is G2? These are the composable pairs of arrows. So they are pairs, G1, comma, G2, such that I can put them in the opposite order, such that the target of G1 is equal to the source of G2. Okay. And you could continue this sequence of manifolds, the single arrows, the composable pairs of arrows, the composable triple of arrows, and so on. Okay. And the more arrows you have in your tuple, the more maps there are to go one level down, because you could choose to compose in many different ways. So for example, here we have 3 maps. These are called del 0, del 1, and del 2. Okay, and del 0, so these are labeled, actually, I'm sorry, but let me just change the indexing to be more consistent with what's in the literature. So the target of G0 should be the source of G1. And yeah, so del 0 sends this to G1. Del 2 sends this to G0. And del 1 sends it to the composition. G0 compose G1. Okay, so there are 3 ways to get a single arrow from a pair of composable arrows. Either you just forget one of the 2 arrows, those are the 2 extreme cases, or you compose the arrows, and then you get a single arrow that way. Okay. And the nice thing about this is that, this type of structure is called a simplicial manifold. This is an example of what's called a simplicial manifold. Because you can kind of think of this as being points, this as being 1 simplices, this as being 2 simplices, and you could think of these as being the boundary of the 2 simplex, you know, the triangle, and there are 3 boundary faces of the triangle. And just like in homology, just like in the description when you take a topology course, when you have a simplicial complex, you can produce a differential from this, and you can produce a cohomology theory. So from this, what we can do is we can produce a complex. Let's say we take, for functions, I'll use the notation O of x. For functions on G, I'll use O of G. Functions on G2, I'll use this, and you continue this way. And this is source and target, but let me just give them the names del 0 and del 1. And by taking the alternating sum of these maps, the pullbacks of these maps, we get a differential. So this is delta, delta, and so on, where delta is by definition the sum minus 1 to the I, del I, pullback. Okay, so we get the so-called groupoid complex. And this leads to the so-called groupoid cohomology. Okay. All right, and this condition here, you can see that it is saying that the value of this map on the 3 faces of the triangle are all related. And so the equation star is equivalent to the condition that delta rho is equal to the trivial element. Normally you would say it's closed. Normally you would say delta rho is equal to 0. But because this is a group, it's not 0, it's 1. Okay. So to say that we have a representation on this groupoid is saying that we have a one cohomology class with values in this coefficient group. So this means that the final outcome of this board is that the representation rho has a class of rho, which is in the first groupoid cohomology with coefficients in the group, in GL. Actually, let me change the general G back to the actual groupoid that I'm interested in, pi 1 xd with coefficients in GLRC. Okay. Okay, so this is what you would call first non-abelian groupoid cohomology. Non-abelian because its coefficients are not an abelian group. Okay, so the representations form an elements of the and don't be confused. This cohomology, whenever you take coefficients in a non-abelian group, it's always problematic. You shouldn't think this is not a vector space; it's a set. Actually, it's what's called the moduli space, or it's the category of representations. But when we take H1, when we take the class, this is the isomorphism class of this representation, and this is otherwise known as the character stack or character variety or representation variety.
So, can I ask a question?
Yeah.
So when we define what rep of this pi 1, that was not representation in this sense, right? It was representation with values in, so I don't know, section of vector bundle and so on.
Yeah. Okay.
So this is not directly related to what we are considering.
Okay, so so what I'm trying to sweep under the rug is the following. I'm going to explain what I'm sweeping under the rug, which is that what I've done here is I've trivialized the vector bundle. The vector bundle of rank R, I've trivialized it so that every parallel transport is really just a matrix. In general, what you would have here is not a single group, but it would be all possible isomorphisms between fibers of the bundle. And that forms a groupoid over X. So in general here, what you would need to do is you would have to define GLE, which is a groupoid over X. And basically this would take the place of the right-hand side. That's all. That's the only modification I would have to make. The point is that, since we're interested in what's happening near the pole, we can trivialize the bundle near the pole and just study that. And so I prefer, for the talk, just to trivialize the bundle and say that every parallel transport is really just a matrix, an invertible matrix.
Excuse me. Could you please explain again how do you get this cohomology class from the representation?
Yeah. So it's from this. So you see, this equation. I could think of it as saying that the value of rho on delta 1 is equal to the value of rho on delta 0 multiplied by the value of rho on delta 2. Okay. And so if you bring everything to one side, then you're just going to get rho of delta 1 of, what's the representation called? I need a name for the representation. Suppose that P is a representation. Okay. Then you see this delta 1 star P, this means that we are going to evaluate P on G1, G0, right? And then I bring these over. Okay. And so this is exactly what the what this delta, how this delta is defined. You see that you have a +1 here, a -1 here, and a -1 there. Okay, and yeah, sorry. I mean, I wrote this. This is like a summation notation where we're adding things together, because that would be like an abelian group. Here, instead of the plus notation, I'm using the product notation and the inverse notation, but it's exactly the same operation. So it's really being in the kernel of delta. So this is like saying that, yeah, hopefully that makes sense. Oh, I'm sorry, I got all confused. So, sorry, rho is the name of my representation. I'm sorry, this is much simpler. I'm going to blame it on jet lag. This is it.
It's a non-abelian.
So we have, this is delta rho. This quantity here is delta star, delta star rho. Okay. It's rho, yeah, hopefully that makes sense.
Non-abelian cohomology.
That's right, non-abelian groupoid cohomology. This would be a non-abelian version of the usual groupoid cohomology. And that's the coefficient. I could put a...
You can also define the higher deltas, higher degree.
The higher deltas are well defined, but the problem is that, as usual, the higher, it's because when you have a simplicial thing, it's better to keep it simplicial instead of converting it into a complex in the case of non-abelian cohomology. But yeah, for now, we just deal with this. Okay, so
Sorry, it's not quite the same delta that you had there.
it's not exactly the same because these are functions, and so this would be a sheaf of abelian groups,
Right.
and so the operation would be plus, which is the summation here. But if the operation is different, then I put a product here. Okay, and right. Okay, so so let me give an example based on the assignments from last time, based on the exercises from last time. So we had this example. Oh, I'm sorry. This is slightly different from the example because this has a pole of order 2. And the fundamental solution to this, which again, well, let me just write it. So this is e to the -1 over z. Some function, which I'm not going to tell what it is. This. So the general solution would be a linear combination of these two columns, the general solution to this equation. Okay, where f satisfies this equation. It satisfies z squared f prime is equal to f minus z. It satisfies an inhomogeneous first order differential equation. And you can actually write this in terms of special functions. The exponential integral, you could write the solution f of z in terms of special functions, but I'm not going to do that. That's not important for what I'm talking about. So notice what this solution looks like. So remember what this means. This is the parallel transport along a path which goes from some initial point. How do I know where the initial point is? Well, I would need this matrix to be the identity at the initial point. But, let me just say that both of these two columns, they're clearly linearly independent. And they each solve this equation. So this is what you would normally call a fundamental solution to the system of equations. But if you notice, when you look at it, there's a few things to remark. This thing has an essential singularity. So this is badly behaved. Okay? And this thing also has essential singularity, and it also has a branch cut singularity. So it's not even single valued, this function which satisfies this equation. So this thing is, we're used to this in differential equations with singularities. We're used to saying that the solution, right, is this really badly behaved singular function. And so, so you could either just accept that, or you could view it as a problem. But this is not the representation. The representation, this would be P going from P along some, well, okay, so this is supposed to give us a representation, but a representation of what? Which groupoid would this be a representation of? Stokes. So this is a representation of Stokes. And the representation would be this. It would be P, Z, U. Remember, Stokes 2, it looks like C cross C with coordinates Z and U. Okay? And the source of this, this is an arrow going from Z. That's the source. And the target would be e to the zu z. So it's different from the one that we studied in the exercise session. So this p of zu, what is it? Well, we did this calculation before. You need to pull back the fundamental solution matrix by the source and invert it, and then you need to compose it with the pullback by t. And this thing, right, and this thing is a holomorphic map from STO2 to GL2C. This is the true solution. This representation is the true solution, and you can kind of see what's going to happen. If you pull this back by source is just Z. So you just plug Z in here and you invert this matrix. And you put it here. Okay, that will give you in this top corner e to the plus 1 over Z. Okay, and then when you multiply that by the target pullback of psi, the target pullback would be to substitute this expression into Z. Okay? And when you do this product, you'll see that this inversion makes it so that all of the singular behavior is canceled out. And also the log branch cut is canceled out. And so this becomes a single valued invertible holomorphic matrix which satisfies delta p is equal to 1. Okay, so I'm not doing the calculation, but you can easily do it. Okay, and this is I would say this is the true solution. Okay, now I want to tell you something just for your own education, especially for the young people here, that there is something very bizarre that happens when the pole order is greater than 1. Okay, and that is the following. So when you're faced with this problem, right? Let's say you had to write down an actual solution here, and let's say you didn't know anything about special functions. Then how could you solve this? One way to do it would be to try to solve by power series. So let's try to solve by power series. So we'll call that f hat of z. So this is now a power series that satisfies this. And then it's easy to solve. Then you can solve that. F hat of z it's a very amusing expression. As a power series in powers of n, the coefficient is n factorial. Beautiful convergent series, right? Okay. So we get a fundamental solution which has 0 radius of convergence. 0 radius of convergence. Okay, and this is generic. This is the behavior of poles of order greater than 1. We always get power series solutions with 0 radius of convergence. Okay, and there are many sophisticated analytical techniques, okay, for trying to resum this divergent series to get an actual solution to the system. Okay, this goes by the name, for example, Borel resummation, okay, which is a very nice thing. But think about what this is saying. So this is a formal solution. So let's plug it in here. We get a formal solution psi. We take the formal solution f hat. We put it into psi hat, and we put it into p hat. So this will be now a power series in 2 variables, z and u, on Sto 2, sorry. Okay, but we already know what the solution is supposed to be. The solution is supposed to be guaranteed by the theorems. It's supposed to be single-valued invertible holomorphic matrix. So what can we say about this power series? It has to converge. This converges. And we get PZU. Okay, so this was one of the remarks in our Stokes Groupoids paper, which hasn't really been followed up, mostly because I don't really understand it that well, and no one else seems to understand it. But this seems to be a way of taking a formal solution and just snapping your fingers and resumming it. Who knows why it works? So I'll put this as a question for the future. Any questions about this? Yeah.
So P hat is a converging not converging, is a series in C or GL to C?
Oh, I'm sorry.
And I didn't understand why it is supposed to converge. Okay, it's not a...
No, I mean, that's a very important point of what I'm trying to describe in these 2 lectures. This thing is horrible, this so-called fundamental solution. Why is it horrible? It's because we're trying to write it as a function on the base curve. The solution is not on the base curve. The solution is a parallel transport operator, which assigns to every path a matrix. So it is defined on the groupoid, not on the base curve. So when we do this operation, we get the representation of the groupoid. And this is holomorphic always, with no singularities. Right? Why? Because it's a representation of this groupoid. We identified the correct groupoid on which it is holomorphic, single-valued, etc. Okay? So it's automatic. If you do this calculation, then you know, for example, if you found this essentially singular with a branch cut function in terms of special functions, and you plugged it in here and you plugged it in here, all of those branch cuts and all of those singularities would disappear, and you would just get. So Jan did an example like this, where it was singular on the base curve, and he pulled it back to the groupoid, and it was just, holomorphic. Does that? So we know that it is holomorphic a priori. And you can, I've done this computation and gotten these nice convergent power series in 2 variables, and it's quite remarkable that the whole thing works. Was there some other question?
Yeah, I was just wondering whether it's then possible to use that, like, to resum the f hat, like, in terms of the original variable c, or does it help, like,
So so when this converges, what that means is that, well, you're going to have an open set around the origin in the set U10, where you will have a holomorphic matrix-valued function. And what is that matrix-valued function? It's all of the possible parallel transports between those points. So what that means is that if you were interested, for example, in the initial condition here, let's say this is the complex plane, z0 and z, and if you wanted to do a parallel transport from your preferred initial condition somewhere, you could just evaluate this. You just evaluate it.
I don't know, maybe that's not a good question, but now what's the interpretation of those Stokes matrices now?
We're going to get to that, yeah. Okay, so yeah, that's actually the next line. So you're very you can see through, and you can also reverse. So Stokes data. So when you are faced with a connection like this, there is a standard classical procedure for identifying, for classifying these. And what you do is you extract certain invariants, and the most famous invariant is the monodromy. And the next is the so-called generalized monodromy, which is a sequence of matrices in the upper and lower triangular group. And these are called Stokes matrices. Okay, and I can't give a course on Stokes matrices. That's kind of what I did in 2014. But the standard analysis, so the standard analysis of this connection is to compare it with what I'll call nabla knot, which is a connection very similar to this one, but which is diagonal. So this here, this is a diagonal connection which agrees with nabla in its leading order singular behavior to leading order. So, for example, what we could do here is we could take nabla knot to be d plus minus 1, 0, 0, 0, z to the minus 2 dz. Very similar to what Jan did in the exercise yesterday, okay, where I don't have this sub-leading order in the pole. Okay, now, right. So this means that if I have my groupoid here, pi so 2, right, and I have my, let's call it c to the r, c to the r. So for every arrow in the groupoid, I have a matrix, which we called P, and I'll put a subscript nabla, because this is the representation for the connection nabla. But now I have a nabla knot. I have another representation. I have this simpler representation, P nabla knot. So now I have two representations of the same groupoid, because they have the same leading order behavior. Okay? And this means that I can produce sigma, which will be the ratio between these. P nabla knot inverse. And this is an automorphism of, well, this is, yeah. So I take the matrix that the simpler representation provides, inverted, and product with this. So this is a, so you can kind of say that this is, what is sigma? Sigma is kind of the data that you would need to go between these two representations. So whenever you have two representations of a group or of a groupoid or whatever, you can always take the difference between them or the quotient of them. And what you'll get is a one cocycle. You'll get a groupoid one cocycle. So this is a one cocycle with values in the automorphism of the simple connection, P nabla knot. Okay, this is a general fact. Whenever you have two representations of anything, you can take the quotient and you can describe one of them in terms of as a one cocycle with values in the automorphisms of the base point that you decided to choose. So this, okay, so this is in H1 G, with coefficients in automorphism of P nabla naught. Okay. And here's the key point. This is the point that confused me for the longest time, and it is that, you see, the fact that nabla and nabla naught agree to leading order at the pole, it means that this quotient is equal to 1 at the pole. They're equal at the pole. Okay. And what that means is that this 1 cocycle is trivial at the pole. So it's actually a relative groupoid 1 cocycle. Let me so this is saying that that this groupoid cocycle is a relative non-abelian groupoid 1 cocycle. Okay. And this here, this is the space of Stokes matrices. And so you can interpret this thing as giving a sequence of Stokes matrices. Okay, now I don't really have time to explain why this is exactly equal to Stokes matrices, but here's a hint. Let me just draw a picture of the complex plane with the divisor. Oops. So because you're doing a relative cohomology, relative to the groupoid over the divisor, right, you have a kind of excision which allows you to replace this divisor and blow it up in the real category so that it becomes a circle. And you can say that this relative cohomology is the same as the relative cohomology of C relative to this circle boundary. And the good thing about this expression for the same group, right, is that we can now cover it with open sets. We can do a check open cover like this. This is explained in our paper. Okay. And then you end up with a check 1 cocycle description of this 1 cocycle. And it turns out that this sequence of data is exactly the Stokes matrices, the upper and lower triangular matrices. Okay. So the point of this course is not really to give a full description of Stokes matrices, but I feel like for your education, you should really know about these hierarchical poles and their bizarre behavior. Okay.
Can I ask a couple questions?
Yeah, go ahead.
So in this picture with the real blow-up,
Yeah.
usually, this is the lean description of the sheaf with filtrations.
Yeah. So there is a came apart. Keep going. Yeah. What about Deling's description?
Yeah, I just want to ask, can you see this sheaf with filtrations in this description?
Yeah, you can restrict the representations here, and you can study what do they determine along this boundary circle, and you'll see these structures. The problem with that approach and the reason that it is so analytical, because if you look at their proofs, there's a lot of kind of exotic analysis involved. It's because they're temporarily forgetting all of the complex structure because they're doing this real-oriented blow-up, right? And so because of that, they need to re-add it back after the fact, and so it ends up being kind of a complicated way to go about it. But yeah, you can extract it from this picture.
I wanted to ask another question too.
Yeah. Go ahead.
For example, if you take the Airy function, for example,
The Airy
the
function?
equation that gives it the Airy function.
Yes.
If you try doing this diagonalization, you end up with a fractional power of z, right?
Yeah.
Does your description?
In the case of the Airy equation, and this is worked out in the paper in the second to last chapter, okay, you're going to get all kinds of fractional powers here in addition to being log. There's no branch cuts in that case, but there's essential singularity at infinity, and there's. So when you pull that back, everything's fine. Everything goes away. There's no fractional powers of any kind.
So is it like I Are you taking Stokes groupoid relative to a cover, or?
No, there's no cover needed.
Never needed.
It's a representation on that curve. It's a representation of a Lie algebroid, and you need to integrate that to a representation of the correct groupoid, which in that case would be Sto 2, I think. It's a second order pole at infinity, if I remember correctly. You see, like all of these, there's a lot of singular type behavior, but you need to be able to distinguish between the base curve and the groupoid on which the representation is defined. Once you know what the groupoid is, then everything will be smooth there. Okay, so I want to describe something, a different idea, which is related to everything that we've developed so far. So, and this is about iso-monodromy. Do I have until 11:10? Yeah. Okay. So, okay, and this, the benefit of describing iso-monodromy is that it's going to tie in with the generalized Kähler picture that I'll talk about in the rest of the course. So let's talk about, oops, my skin is very dry up here. Thanks for bleeding. Don't be bothered if no one faints or anything. So what is iso-monodromy? So given a family of curves now, x sub t with a divisor, this is a divisor. So this could be a sum of points which depend on t. So let me draw a picture of that. So imagine that we have like these curves with a divisor on it, okay? And imagine that we have a family of these curves over some base. Let's say this is pi, this is the base s, this is the total space x. And the divisor also is a family of these divisors. So this is a variation of the complex structure of the curve. So this is a family of curves and a family of divisors. So these curves are not isomorphic as complex manifolds, but they're topologically equivalent. Okay. So, and I should, the base is some complex manifold, S. And imagine that I choose a path in the base, gamma. Yeah. So the question of iso-monodromy is, what is the relationship between flat connections, meromorphic flat connections on this curve, and meromorphic flat connections on this curve, right? There is an idea that meromorphic flat connections are just flat connections, so they shouldn't really depend on the complex structure so much. So they should have the same category of flat connections. They should have the same moduli space. In fact, what you get is, so associated to this family, this gives rise to a family, let's call it M sub t, of moduli spaces of flat connections. Oh, it's because I didn't use the wiper. I forgot to use the wiper. I'm not experienced with this. Anyway, now it's too late. So we get this family over the same base S, and these are now these kind of much larger dimensional spaces, M sub t. Okay? And iso-monodromy is the statement that this family of moduli spaces has a flat Ehresmann connection. It's a flat fiber bundle. So iso-monodromy is equivalent to the statement that this family has a flat so-called Ehresmann connection. It just means that it's a flat fiber bundle. And it means that if I have a flat connection, an isomorphism class of flat connection, at the initial time in the path, then I can drag that horizontally to a unique flat connection at the end point in time. Okay? So, for example, if we have a family D, this is the famous example, K equal 1 to N, where Pk of T is the, let's say this is a divisor on P1. So suppose that we have a connection, a family of connections on P1, and we allow these points to vary in time, and we would like to, we would like to drag this connection to nabla of 1 in such a way, in an iso-monodromic way. So what that means is that we have an initial connection, and we would like to follow this flat connection and get the corresponding flat connection on P1 with the new positions of the poles.
So maybe I get confused about the following. In principle, I probably know a little bit of what is an iso-monodromic deformation, but in this formalism, how do you, so you say we need some flat connection, but what does it mean to be iso-monodromic?
Yes, so the reason that people called it iso-monodromic is because when you, let's say that you're given an initial connection, nabla naught, you can compute the monodromy matrix around this curve. Okay? And the idea is, they knew that we should be able to drag this connection over here because these are diffeomorphic. So if you forget the complex structure, it's clear that this connection here determines one here. Okay? So they said, well, how can we describe in a concrete way how this connection should vary? And the way they said it is they said, well, we should vary the connection so that at every time the monodromy around this divisor point is the same. So that the monodromy remains constant. That's iso-monodromy. So that's one way of thinking about how to do this deformation. But anyway, that's the reason that it's called iso-monodromy. So what you want to do, the question is, so i.e., how should the connection matrix AK vary with T? Okay? And the solution to this question, the solution to the iso-monodromy problem was found a long time ago, more than 100 years ago, by Schlesinger. So we get the Schlesinger system, okay, which is this. It says that the way that AJ should vary with respect to PK, okay, is that we should have the commutator between AJ and AK divided by PJ minus PK when J is not equal to K, and it should be the sum of J not equal to K of the commutator AJ AK divided by PJ minus PK when J is equal to K. And in the case where there are 4 singular points on P1, and if the group is GL2, this equation, this system of equation, is equivalent to the Painlevé 6 non-linear ordinary differential equation. So if you try to write, if you have 4 of these matrices, you have 4 of these matrices at the 4 poles, okay, and you want them to vary in GL2 in such a way so that as these points move, the monodromy of this connection remains constant, the monodromy matrices at the 4 points, then they should satisfy the Pale of A6 nonlinear ODE. Okay, so that's just a very brief introduction to iso-monodromy, and in the last 1 minute, I should explain that, you know, how do we see this and improve this? We should have a functor from the representations of pi 1 x naught d naught to the representations of pi 1 x1 d1. If we could find this functor, or let me call it capital phi, okay, then you know, we should have a way of seeing how to transport a flat connection from one curve to the other. And the interesting solution is that we look at this total space. So we consider the total space xd of the family, and we consider the twisted fundamental groupoid of it. So what does that mean? That means that we are now going to consider paths of this. All possible paths of this.
You have to start and end at these two?
Well, so we know that this, because x maps down to the base, the paths in the total space can be mapped down to the paths in the base. Pi 1 x. Actually, this is a surjective map. It's a surjective submersion. This is a surjective submersion. Okay, this is a surjective submersion. And here we have our given path, which we are interested in dragging the connection along. And so what we can do, what do I call this map? Pi lower star. So we can look at pi lower star inverse of gamma. Okay, and this I'll call Q gamma, and it's a submanifold in there. And Q gamma, what is it? I've drawn it here in orange. Q gamma is all paths in the total space which map down to this path, which go from the initial, therefore they must go from the initial fiber to the final fiber, okay? And they must remain everywhere tangent to D. So this means these are logarithmic paths, or paths, they have to be tangent to D. But in any case, this is a groupoid. Like, I haven't really described this groupoid, but what I'm saying is that there is a Lie algebroid over here, which is T. This, by definition, this is the integration of Tx minus log D. So this is another Lie algebroid, but it's defined on the total space, and it's consisting of vector fields which are not vanishing on D, but which are tangent to D. And so if you integrate those vector fields, you get paths which, if they lie on D, they must remain tangent. So there are some paths like this. Okay. That's what this thing is. This is a manifold consisting of paths. These are paths joining x0 to x1. Okay? And therefore, this maps, there's a source to this, and it maps to x0. And there's a target to this, which maps to x1. And here we have pi 1 x0 d0. This is a groupoid over x0. And here we have a groupoid over x1. And of course, if I have a path in here, I can act. I can take one of these paths and I can compose with this, or on the other side. So that means that these groupoids act. This groupoid acts on this space by composition, before and after. pre and post composition. And this is what we call a Morita isomorphism, or a Morita equivalence. Okay. So a Morita equivalence is a manifold which maps. This is a Morita equivalence between the groupoids. Okay. And what does it mean? It means we have a manifold that maps to the two bases in such a way that this groupoid acts here, and the way that it acts is principal. So this is what's called a principal bundle. This map here, T, is a principal bundle for the action of this groupoid on this space. So this is a bi-principal. It sounds complicated, but it really isn't. Bi-bundle. Because it's a principal bundle on both sides. You can compose on before and after. Okay? And because of this space, we can take our representation, we can pull it back, and because there's an action of this groupoid, we can quotient it down here. And that's our functor. So then the functor phi that we are looking for is just S pull back, T push forward. Okay. And we get an iso-monodromy functor. And okay, I'll make one last statement and I'll stop. I just want to summarize what I did in this work. That's a good point to stop. Okay, so what did we obtain in the end? So this implies that we get an improved iso-monodromy functor, which looks like this. I'll just write it like this. Pi less than or equal to 2 of S mapping to G. Now this is impossible to understand. So these are, this has objects, this has objects which are points of S, the base. This has one morphisms, which are paths in S, and it has two morphisms, which are homotopies in S. And it's what's called a two-groupoid. Homotopies in S up to equivalence. And this is the category where the objects are the groupoids. The one morphisms are Morita equivalences, like this. And the two morphisms are isomorphisms between the spaces that define the Morita equivalence. Isomorphism of Morita equivalences. So whenever you have a family of curves like this, xd over S, we obtain this natural map. Okay? Each point of S has a curve associated to it. That curve has a groupoid associated to it. That's this. That's how the points are sent to the groupoids. And whenever you have a path between 2 points in the base, we get, by this construction, a Morita equivalence between the initial and final points of the path. So we get a one morphism. And then if we have a homotopy between paths, the corresponding spaces, Q, are isomorphic. Okay? And from this, you can deduce everything that you need to know about iso-monodromy and what happens when you move the path along which you are doing iso-monodromy, right? So you could even imagine taking the two-sphere, right? You could imagine doing iso-monodromy along a path in the base two-sphere, and then you could imagine sweeping that path around the two-sphere, right? And getting the morphism of the representation category. So this, a lot of times you see these results about why the character variety has these bizarre automorphisms, and that will come from the second homotopy group of the base manifold family of curves. Anyway, okay, I just wanted to give you an idea. It's a little bit too much.
And then we should
Thank you.
now try to.
Sorry.
No, any brief questions?
So why do you call it this functor Morita equivalence? Is there some obvious way that it's similar to a Morita equivalence?
Okay, so when you have, when you have these groupoids related by these bibundles, okay, the main reason why it would be called Morita equivalence is that it induces an equivalence between the representations. So the representations of this groupoid can be transported to representations of this groupoid. And so for that reason, it's called Morita equivalence. Yeah, because in algebras, that's how they did it. So anyway, yeah.
Okay. Any more questions or comments?
I mean, just very briefly, sorry, when you consider these moduli spaces for the iso-monodromic, you're considering moduli spaces of meromorphic connection with poles there at each fiber over S.
Yeah.
So the polar divisor, with polar divisor, what is it? The poles are bounded by D at each point.
Yes.
That's it or just more? Because that's big, right?
Slower, I didn't hear what you said.
What?
I didn't hear what you said.
Sorry. So I was thinking maybe there are more parameters to somehow restrict the moduli spaces, of connections with like more restrictions on the principal parts of the connections or stuff like that.
So what I described here
Yes.
was where, yeah, so I swept that under the rug because I'm assuming here for this discussion that the divisor is simple.
The divisor is simple.
Or poles of order 1.
Okay.
If you have poles of order 2,
Yes.
right, then what you would need to do is you would need to fix the base point, nabla knot, along this. Right? Because the Stokes matrices were described as a relative cocycle. So you would need to fix the behavior along the pole of this initial base point connection. And then you would get this parallel transport as well. Yeah. That hasn't been written, and we should read it.
Okay.
But it's a good
All right. Yeah, probably we need to wrap it up. Thanks a lot, Mark.
Thanks a lot.